To teach a modern artificial intelligence to recognize a simple object, you need sprawling server farms churning through millions of training images and consuming massive amounts of electricity. Yet, a bumblebee can navigate a complex three-dimensional environment and solve dynamic problems using a brain the size of a sesame seed, running on a fraction of a watt of energy. Physical size doesn't automatically equal superior intelligence. An elephant has a brain 2.5 times larger than a human's, yet many still die of starvation when their teeth wear down. It's the efficiency of the connections that matter, not just the volume of the tissue. The next leap in computing power likely won't come from building endlessly larger silicon chips. It will come from figuring out how to harness the extreme physical efficiency already perfected by biological networks. Right now, the dominant trend in tech involves trying to implant silicon technology into human biology to enhance our natural capabilities. But at Cortical Labs, a team of scientists operating out of Melbourne, Australia, decided to completely invert this engineering question. Instead of putting technology into a living brain, they are taking living brain cells and installing them directly into computer hardware to act as a processor. This move, shifting biology from a medical patient to an engineering component, is the core of a field called synthetic biological intelligence. To build a biological chip ethically, you don't harvest tissue from brains. Scientists take ordinary adult skin or blood cells and transform them into pluripotent stem cells that can be reprogrammed into almost any type of tissue in the body. From there, these stem cells are coaxed into becoming living cortical neurons. They are carefully grown over a dense grid of microscopic metallic electrodes, creating a direct physical interface between biology and machine. Left alone in a dish, these neurons will naturally fire and communicate, but isolated without any sensory input from an outside world, they are essentially talking in the dark, producing meaningless electrical static. For a biological processor to be useful, it must be embodied. It needs a simulated external environment to perceive, react to, and care about. To prove that this biological system could actually learn, scientists wired their lab-grown processor to play the classic arcade video game, Pong. This presents an immediate engineering challenge. How do you motivate a cluster of unfeeling lab-grown cells to play a video game? The answer lies in the free energy principle. This is a biological theory stating that living systems will inherently work to minimize unpredictability and chaos in their environment. The scientists created a closed feedback loop. Whenever the Pong paddle misses the ball, the system injects violent, unpredictable electrical static into the neurons. But when the paddle successfully strikes the ball, the system feeds the neurons a predictable, organized, and soothing electrical signal. Driven entirely by this natural desire to avoid chaos, the cells physically reorganized their connections. Within 5 minutes, they learned how to successfully move the paddle and hit the ball. Traditional machine learning algorithms require thousands of data cycles and massive power consumption to learn a task like this. This small cluster of cells achieved it in minutes, demonstrating the vastly superior learning efficiency inherent in Wetware. Seeing cells learn to play a game instantly raises an ethical anxiety. Did scientists just create a conscious, trapped entity suffering in a petri dish?
To answer that, we have to recognize the strict scientific boundary between intelligence and consciousness. Intelligence is the ability to process data and solve problems. Consciousness is the subjective experience of self-awareness. We know these two traits can exist separately. Take the medical phenomenon of blindsight. A person with damage to their visual cortex might perceive that they are legally blind, but if you throw a ball at them, they will catch it on reflex, processing visual data without any conscious awareness of the ball. The biological computer operates like that reflex. It is not a sentient being, but a highly complex engineering tool capable of advanced problem solving. This technology integrates into a framework called heterogeneous compute, a hardware strategy where a computer uses multiple specialized types of processors to solve a single problem. Imagine a system that simultaneously utilizes a silicon chip for heavy math, a quantum chip for cryptography, and a biological chip for real-time, low-power learning. This also provides a new path for healthcare. Researchers can now observe how drugs affect active brain cells rather than dormant tissue. When scientists introduce an epilepsy model, the cells fail at Pong. They can test chemicals in real time to see which drugs stabilize electrical signals and restore gameplay. Moving biology onto a chip turns the human brain into a testable platform, allowing us to see exactly how neurological disorders disrupt the flow of information and how we might intervene to fix it.